Okay, welcome back. I've got new technology now, a new plan for my recordings. Let's see if this works. It's DTC and resource efficiency. And as you can see, the big difference here is that I've got a little window showing me and you, well, especially showing you where we are in the video. And because of that, I'm going to record this as one long video, okay, because you can easily flick through to find the place you want to be at. That's my thinking. That saves me quite a bit of hassle in terms of uploading and mucking around with links and stuff. Welcome to give me feedback on that. If you still prefer lots of short videos, I can do it. But I'm going to try this in one long video. Okay, so here we go. It's chapter 5 of the book, Directed Technological Change and Resource Efficiency. So what's this all about? So we're going to start by thinking about how do we include resource efficiency in the production function. So we're building a macroeconomic general equilibrium long-run model, and we're thinking of labor, maybe capital, but actually we're dropping capital, yeah, and resources, and how they interact to help to produce the stuff that we want. How do we model that? And then, of course, we're going to link that to the supply of resources, to the emissions of pollution, and so on. But at the moment, we're thinking about the production function. Oops. So what have we got here? We've got, I've got to look closely. We've got 4 alternative suggestions for how we could set up a production function, right? So what are they? We've got y is some function of ALL and ARR. So this is an the most general possible production function, given that there's only one product and there's only 2 inputs, resources and labor. We've dropped capital. Because remember, based on the discussion of units and so on, if we've got a physical input, we always need what we can call a resource augmenting technology or productivity level for that input to get the units right. Yeah, if this is workers and this is widgets, then we always need this, which is going to have units, widgets per worker per year. Sorry, this is widgets per year. Yeah. So this is the most general possible production function. So how might we choose to specify it? One way would be as a Cobb-Douglas, yeah? So a very general Cobb-Douglas would be ALL to the 1 minus alpha, ARR to the alpha. And note that we can pull these 2 out and say, well, why don't we define A equals AL to the 1 minus alpha, AR to the alpha. And then we could say, well, that's the same as, with a suitable definition of A times L to the 1 minus alpha, R to the alpha. So this is kind of telling us something important about the Cobb-Douglas, isn't it? It's telling us that increases in this and increases in this, when we take a bird's eye view of what's going on, we can't really distinguish them. Okay, they're both just sort of boosting Y for the same inputs of L and R. We'll come back to that. Next one, Y equals min ALL ARR. Now, you might want to pause your videos very shortly and think about this. What is this production function called and what does this mean? Okay, so I suggest if you don't know that, pause your videos and have a think. Okay, the answer is it's a Leontief production function, right? Maybe I mentioned this actually in the last lecture. I think perhaps I did mention early on, yeah, I seem to remember talking about shoes. But the point is here that we need, for 1 unit of Y, we need at least ALL units of this, and, well, sorry, yeah. For 1 unit of Y, we need at least 1 unit of ALL, augmented labor, and 1 unit of ARR, augmented resources, which means we need at least 1/AL units of labor and at least 1/AR units of the resource. And if we have more than that, if we keep one of these at 1 and make the other one 100, it doesn't help. You know, we still only get 1 unit of product. So you basically need the 2 inputs in fixed proportions. It's like shoes, yeah. Doesn't help having 100 left shoes if you've only got 1 right shoe. You've just got only 1 pair of shoes, yeah. So the inputs are needed in fixed proportions, but we can adjust those proportions if we can adjust these productivity factors, yeah. That's Leontief. Finally, we have this one. Just see exactly what I've written here. So again, you might want to pause your video and think about, what is this production function called? The answer is, it's called the CES, the constant elasticity of substitution production function. And the elasticity of substitution is determined by epsilon, and it turns out that it's equal to 1/1 minus epsilon. So think about that. If epsilon is 0, this suggests then that the elasticity of substitution should be 1, right? Does that make sense? Well, then actually we end up with something we can't make sense of. We need something called L'Hopital's rule, which would tell us, if I was going to go through it, that this is actually, when epsilon is 0, this collapses to the Cobb-Douglas. But actually these gammas and 1 minus gammas turns into 1 minus alpha would be gamma, and alpha would be 1 minus gamma when epsilon is 0. What about when epsilon is 1? Then the elasticity of substitution is infinite, which means these are perfectly substitutable. And if we put in epsilon equals 1 here, we just have a linear production function, don't we? Y is gamma ALL plus 1 minus gamma ARR, which is exactly perfect substitutability. Epsilon becomes negative, then eta gets smaller and smaller, yeah. There's less and less substitutability. And in the limit of epsilon going to minus infinity, there's no substitutability, and this turns into Leontief. So this is super flexible. Okay, this is a super flexible production function. Of course, it's still restricted. The elasticity of substitution is always constant. Okay. I'm going to pause here and close Outlook. Sorry. Okay, I believe that I'm recording again. So, general production function, 3 specific ones. Let's think about what these are good for. So, Cobb-Douglas. This is kind of nice, actually, Because remember, in the Cobb-Douglas, given this production function, we get constant shares, constant factor shares. And remember, when we think of labor and capital, we see that the factor shares of labor and capital tend to be more or less constant over time. The same is true of labor, capital, and natural resources, or labor capital together, which is what this is, and natural resources. They tend to be rather constant over the long run. And we can see that if we plot again, as we've done before, against time on a log scale, y WR, or actually, if we allow for a population growth, it should be Y over L. WR and R. Oh, sorry, no. We either need R over L and Y over L, or Y and R. Let's just do it like this. So Y is the total value of everything we produce. WR is the resource price. R is the resource quantity. When we look at very long run global data, this is what we tend to see, okay? Which if we multiply these two together in logs, that means adding the slopes. It turns out that WR times R grows at the same rate as Y, which means that WRR is a constant fraction of Y. The levels here mean nothing, yeah, because it's normalized, but it's all about growth rates. The growth rate of WRR is equal to the growth rate of Y, which means WRR is a constant fraction of Y. The factor share of resources tends to stay constant. Metals, fossil fuels, etc. tends to stay more or less constant. And the Cobb-Douglas seems to be capturing that. But at the same time, it's telling us that there's no point in trying to save resources by boosting AR, resource efficiency. That's kind of super counterintuitive, isn't it? But the reason is that one way of looking at it is if we boost AR, then it gets more attractive to use resources. So when AR gets bigger, effective resources get cheaper, so we use more. But is this really good enough? Is this really what's going on? This might fit the aggregate data, but it doesn't really tell us what's going on at a more detailed level. So we really want to have a better idea, or we need to go into more detail. So one thing that tells us this is if we have shocks to resource supply in the medium or short run, if R goes down, if this applies at all times, then there should be no effect on the resource share. But in fact, we know that when there's a shock to R, the resource share goes up hugely if R goes down. This is like the oil crisis. Yeah, if you cut global oil supply by 10%, the oil price will go up, not by 10%, which is what this would predict, but by like 100%. It will double, more or less, in the short run. So clearly in the short run, this is not right. So what we would like to do is build a function that works in the short run and then show how the adaptation occurs in the long run, which tends to mean that we see this for the long run. That will help us to really understand what is going on and help us then to know how to control the system better to get the outcomes we want. Okay, because we want to understand the system better. Okay, why not Cobb-Douglas? The other thing is it's like super unintuitive. Yeah. If we think I talked about cutting oil supply by 10%. Given this function, if alpha is small, which it is, and we'll talk about that in the study questions, I think. I need to adapt my study questions. If alpha is small, if we halve r, it hardly has any effect on y. Okay. If we halve r, it hardly has any effect on y. But again, we know in reality, at least in the short to medium run, if we say halved oil supply globally, it would be an absolute catastrophe in the short to medium run for global production. You would lose like almost half of global production. It would be incredibly hard to adapt in the short run. Okay, so what is going on? And if we remember Solo's mechanisms, what might be going on? We might be raising AR. We might, if R goes down, how would we adapt to that in the longer run? In the short run, it's a catastrophe. We might raise AR so we can make the same production with less R. Or, but again, to capture that, we need a different production function. But it could also be that we're changing, we have multiple products and we're shifting away from products that need a lot of R. So we're reorientating the economy away from those products. Those are the kinds of questions we want to be able to answer. How do we, in practice, adapt to changes in resource supply? And what are the implications for policy? Okay, so what about Leontief? So this captures the intuition, yeah. If you cut R, then if you cut R by 50%, you're going to cut Y by 50% until you can either get R back up or get AR up. Okay, so this is capturing the Solo mechanism that it must be when R goes down, we can boost AR in the long run. In the short run, we're going to lose a lot of production. In the long run, we can compensate. But this is very extreme. This one, we can have the same thing, but not quite as extreme. If we set eta equal to, say, 0.1, so epsilon then would be, what would that be? It would be like -10, wouldn't it? Or -9. 1 minus -9 is 10, so eta will be 0.1. Then we have some elasticity of substitution between R and L, but not much. So if we have a short run reduction in R, in the short run, we'll have a lot of drop in Y. In the long run, maybe we can raise AR. So this is a really nice production function to evaluate that mechanism. Okay, that I don't remember which one of the order it was, the Solo's mechanisms. Let's say it was the first, the Solo's mechanism. Okay, I see I've almost gone out of picture here, but hopefully you can see that. Okay. Right. So yeah, I've gone behind the slides a bit. The CES, what values are possible for epsilon? The possible values are, in mathematical notation, we can write epsilon must be in the interval, what is it? 1, or, oh, sorry, I'm making a mess of this. Epsilon must be in the interval -infinity to 1. Okay. That shouldn't be closed, whatever. Epsilon could go down to -infinity, in which case eta goes to 0, and it could be as high as 1, in which case eta goes to infinity. Okay, this is perfect substitutes, linear production function. This is Leontief. Epsilon 0 is Cobb-Douglas. those are the special cases. A reasonable value for when you have resources and labor as the inputs is something, it's something negative anyway, for sure. And we're going to use -1 because it's nice and simple. But it probably should be more negative than that, -5, -10. So advantages of CES, we're capturing the long run. We're capturing the short run idea from the data that if we cut, for instance, resource inputs drastically, that's going to have a drastic effect on production. But we're also allowing directed technological change to compensate in the long run. So we can investigate that mechanism. Okay, I'm going to pause now, clean up the board, and then we're going to look at this little thought experiment. Okay, so I've cleaned up the board, and now we're going to look at this question. So assume an economy with 10 people on an island. 10 trees per week wash up on the beach. 10 people, 10 trees per week. So the time unit is weeks here, it seems. The islanders have a technology called knives, which allows them to cut the trees into planks. And once they've done that, the planks can rapidly be made into houses. They managed to make 0.01 of a house per week. What do they need more of to boost their rate of house building? Suggest values for the elasticity of substitution between the inputs and values for the knowledge levels. Explain briefly. Okay, wow. So this is based, we're going to assume a CES production function. And I didn't mention this before, but basically throughout the course, I'm going to drop gamma. We don't really need those gammas and 1 minus gammas. They only really come in when we're assuming Cobb-Douglas. But if we're assuming Cobb-Douglas, well, why would you set up the CES in the first place? So we're going to drop those gammas. So then we've got this. Now then, what is Y? Y is 0.1. Let me check whether that came onto the picture. Yeah, it did. Okay. Y is 0.1, isn't it? 0.01 houses per week. What is R? R is 10 trees per week. What is L? L is 10 people. So what are AL and AR? And what's epsilon? Well, the short answer is we don't know. Okay. But if we do some thinking, we could come up with some suggestions. So, where to start? So, the key thing here is to think about the technology. The technology is knives. We've got 10 trees washing up every week, and we've got 10 people each with a knife. Okay. How are these trees like in short supply? Are they cutting these trees up into planks in half an hour and then sitting around for the rest of the week? Or are they hacking away with their knives and trying to make use of these trees, and the vast majority of trees are piling up unused? Okay. 1 tree per person per week with a knife. Okay. Seems pretty clear to me that the trees are in excess supply effectively. There's loads of trees. What's in short supply is labor. Okay. So labor productivity is limiting here. So if there's plenty of these, it's almost like we can drop them from the production function. Remember we talked about production functions before, and I said, well, you know, we need air to breathe if we're going to work. We don't put that in the production function because normally, because we know there's plenty of air, you know, we don't need to include it. So here I've kind of argued, if the technology is nice, we don't really need to include this. So then the production function would collapse. The y equals ALL, wouldn't it? Y is 0.01, L is 10. So that means that AL must be approximately 1/1000, right? Because Y is 1/100 and L is 10. ALL is 10/1000 or 1/100. We've got very low labor productivity. It's 0.001 houses per worker per week, assuming an excess, a huge supply of trees. Okay. Can we say anything about AR? Well, we know AR must be big enough to make ARR a lot bigger than ALL. Okay. But we can also think like AR. So if that's all we can say, of course, we don't know much about AR. But actually, we can say a bit more than that, because what are the units of AR? You might like to pause the video again and think about that. What are the units of AR? Well, trees per week, houses per week is the output. So AR must have units houses per tree, mustn't it? So how many houses can you make from a tree? If you're cutting the tree up with a knife or knives and then making a house, of course, it depends on the trees and it depends on the house. But let's just, what do you think? Let's say they're pretty big trees and they're pretty small houses. Then maybe you could make a house from 10 trees. Does that seem reasonable? Maybe 5. Depends how big. Yeah, it's kind of hard to say, isn't it? If we say you make a house from 10 trees, then the AR would be, oops, that's Swedish, 0.1, wouldn't it? Get so used to the Swedish way of writing. 0.1 houses per tree, 10 trees for each house. Okay, that seems reasonable, and that would make it 100 times bigger than AL. So that fits with the story that this is in huge excess supply. And if we stick the numbers in and work this out, well, then finally we need a value for epsilon, right? If we went with Leontief, we'd say epsilon is minus infinity. And then this would fit exactly. Trees would be in massively excess supply. ALL would be 0.01, Y would be 0.01. But if we're going to choose something else, something super simple to work with, which we're going to use in problems and exam questions, if you get one on this, is -1. Okay, then the arithmetic is really nice and easy, and you still get more or less the same. The difference between epsilon -1 and epsilon minus 1000 or something is not that huge. Okay, you still get the same basic type of properties of the model. So we're going to set epsilon equal to -1. So what do they need more of to boost their rate of house building? Well, it's not trees, is it? They need more people. Suggest values for the elasticity of substitution and knowledge levels. Explain briefly. So if epsilon is -1, eta then would be 1/2. Eta would be a half. Okay. Okay. Good. Now assume, and this is where it gets interesting. Now assume that the islanders invented technology called sawmills. And remember, we've dropped capital, so they've also obtained a sawmill. What do they need more of now in order to boost their rate of house building? Suggest new values for the knowledge levels. Explain briefly. So have a think about this. There's a study question on this too with a different model. So hopefully, if you can't work this out for yourselves now, don't worry. But pause the video and have a think anyway. Okay. So if there are sawmills, a decent sawmill, even a pretty rubbish sawmill, 10 people running a sawmill will easily be able to cut up 10 trees in a week, right? They should be able to cut up 10 trees in an hour or 5 minutes if it's a modern sawmill. Okay, so now, given they've got a sawmill, it's the trees that are in short supply, right? Okay, but which of these is the arrival of the sawmill affecting? Is it affecting AR or AL? Well, AR, houses per tree, why would that be affected? It might be affected if the sawmill can make better use of the trees, make nicer planks, get more planks per tree, that will convert into more houses per tree. And that would mean AR going up. On the other hand, it could be that the sawmill creates more waste than the knives, like sawdust and so on, compared to this sort of delicate operation with the knives, sort of splitting the wood and I don't know what. So I'd say it's an open question what happens to AR. I guess, to me, it ought to go up. But let's just keep it constant. Let's assume we get the same number of planks per tree from the sawmill as we do from the knives. Because what is going to change massively is this. Yeah. Given unlimited trees, how many planks per worker per week can we make? And therefore, how many houses per worker per week? Massively more. Okay. Massively more. So let's say, have we given any hint? No. But let's say it's 1,000 times more. So let's say that AR stays the same, but AL goes up to 1. So each worker can cut enough planks, given unlimited trees, to make a whole house per week. Remember, putting the planks together so the houses is quick. That's no problem. It's making the planks that's tricky. So 1 house per worker per week, about labor has become 1,000 times more productive. Okay. Another one for the study questions that I hadn't thought about is what happens if you have a better house building technology, so you only need half the number of planks. Make a note of that, and I can put it in the study questions. Okay. So that was a bit of background thinking, getting you started on thinking about modeling levels of input augmenting technology. What we're going to do now is actually build a proper model where we include incentives to invest in raising these. But I'm going to pause this video, and very soon I'm going to have some lunch, but I think I'll do a bit more. But first I'm going to pause. okay, I changed my mind. I'm going to make 2 or 3 videos, okay, rather than making one huge one. I'm not going to make 6 or 7, but I'm going to make 2 or 3. So I'm going to stop this video now and we'll start a new one. So see you in a minute.